We're in the middle of a
chip war.
chip war.
Chip war.
Tension on the technological front between China and the United States is ramping up.
But why have these tiny, tiny machines created global geopolitical conflict? The simple answer? As we've become more and more reliant on microchips, they've simultaneously gotten harder to manufacture. That's created rising demand for semiconductors for civilian as well as military uses. So, what are microchips? And why are they so difficult to make?
So humans have always attempted to build machines to help essentially augment our own brain's processing power.
From the abacus to the ENIAC computer in 1945, which used mechanical switches and devices called vacuum tubes. But in 1948, William Shockley invented a way to do calculations with electricity, the transistor. So here's like the simplest electrical circuit. Electrons from the battery flow around. Voila, light bulb goes on.
And if you can build those circuits that can open and close automatically or based upon an input, then what you can do is you can build a machine that can process numbers.
So I did. Professor Lamarez helped me use simple transistors to actually do math. Well, 1 + 1 to be exact. They're the simplest transistors available. So I enter numbers with these little switches here, and 1 and 0. And the answer comes out with these lights. The light off means 0, and the light on means 1. 1 + 0, 1. 0 + 1, 1. 1 + 1, 2. Each 1 or 0 is called a bit. It's a single piece of information. 8 bits makes a byte and encodes a number or letter. So a microchip would read Scripps News as 010 and so on and so on. Bytes are the way that engineers measure computing power or memory. And here's how far we've come. This was the IBM 360, an iconic computer from the 60s. It was featured in AMC's hit show Mad Men.
The IBM 360 can count more stars in a day than we can in a lifetime.
Well, the 360s that I worked on ranged from an unbelievable 16,000, a 16K byte memory, 32K to 64K.
That's my dad, Larry Kintish. I guess fiddling with microchips runs in the family. He was a young engineer at IBM in the late 60s.
You read in the program as a deck of cards, and the machine would process additional cards.
The 360 used microchips similar to those IBM built for the Apollo space program.
This was the kind of technology that was on the ships going to the moon. It was a very exciting time to be a young engineer.
The transistors on IBM's microchips were visible to the eye. They were produced by attaching electronics to ceramic squares the size of a postage stamp. They provided 16,000 bytes of memory and could perform 750,000 calculations a second. Today's chips?
This little thumb drive here is 8 billion bytes by comparison to 16,000 bytes.
So how do companies make transistors on today's microchips so small and therefore so powerful? The secret is a technique called photolithography, using light to print complex circuitry in silicon. We visited the National Institute of Standards and Technology in Gaithersburg, Maryland, to see it in action. There, government scientists provide measurement tools for the incredible precision required for photolithography. Our host is Alex Little, the lab's scientific director for microsystems and nanotechnology.
So we're about to go into the research clean room. This tool basically transfers patterns onto the wafer. A typical wafer may have a few hundred or a few thousand chips on it, and those patterns will eventually become the integrated circuit. Here you can see a map of a wafer, and each of these red squares represents an exposure field. So we're actually going to project the mask onto the wafer.
Inside the machine lies the key to photolithography. The silicon wafer has a thin chemical layer that's going to be carved into transistors or other circuitry, and a plastic layer on top of that. The mask is the template for the pattern of tiny circuits. The pattern of light that strikes the plastic makes it ready to dissolve, which chemicals do in the next step, revealing the printed pattern from the template. Then the machine repeats the process to build up layers.
This is just a very simple sort of research test, but in a real microchip, you might have as many as 100 different lithography levels to build up the full chip.
Today's cutting-edge microchips have complex structures carved with features just a few atoms wide. NIST scientists probe chips with light, as well as X-rays, to perfect the photolithography process.
We're looking at these gaps here, these little holes that probably aren't supposed to be there.
So here's a hole.
Correct.
Here's a hole.
Exactly. So a chip that has this many failures typically wouldn't even make it through the manufacturing process.
Ultra-complex, tiny circuits with atomic scale accuracy. That's why the iPhone 14, for example, can perform 16 trillion operations per second.
Every year we do the impossible, and then next year we come back and do something even more impossible. And that rate of progress is why you have the equivalent of a supercomputer in your pocket these days.
As the best microchips have simultaneously gotten tinier, the number of firms that can make them has also shrunk. Dutch firm ASML makes the only lithography machines able to print advanced chips. Its lasers reach 500,000 degrees Celsius, hotter than the surface of the sun. The machine takes months to build and requires 20 trucks and 3 fully loaded 747s to transport, and the last one sold for more than $340 million. But the factory where 90% of the world's high-end chips is made is TSMC, and it sits here in Taiwan. The nation happens to lie on a seismic fault. Analysts believe any sort of disruption, whether from an earthquake or a potential conflict with China, could devastate the global tech world. The U.S. government is working to bring chip manufacturing back to U.S. soil. The president inked a legislative win in August with the signing of the $280 billion CHIPS and Science Act.
America is back and leading the way.
The Biden administration has since announced new restrictions on selling chip-making equipment to China.
So there's an arms race going on right now in computing technologies, which means that there's an arms race in semiconductors.
In a world incredibly dependent on that computing power, conflict over microchips could define geopolitics for decades to come. Eli Kintish, Scripps News.